Hi. In our last lecture, we suggested that it makes sense to split our data into two parts, training and testing. We train the model on the training dataset and then check how well it behaves on the testing one. Ultimately, we are trying to avoid the scenario where the model learns to predict the training data very well, but fails miserably when given new samples. So, we know why we need to split our data. Now we are going to explore how to technically perform a split. For this lecture, we've prepared a clean Jupyter notebook where we will generate data and break the splitting procedure to its building blocks. First, I'll import NumPy. Then, from SKLEARN, model selection, I'll import train test split. These naming conventions are so semantic, aren't they? Now, let's generate some data we are going to split. I'll create two arrays, A and B. Let A be equal to NP A range with arguments 1 and 101. A range is equivalent to the built-in Python function range, but places the generated values in an array rather than a list. Therefore, the result is an array with elements ranging from 1 to 100 included. It is very important that the values inside are arranged. This will help us a great deal to follow what the splitting process has accomplished. All right. Apart from A, I'll also create another array called B, which will range from 501 to 600. Done. Now, let's split the data. We will use the method train test split. Train test split works like this. It takes an array and splits it into two arrays. Easy as that. Let's write train test split of A and run the cell. Exactly as we anticipated. In general, we would prefer storing the result in dedicated variables. So, we can write a train, comma, a test equals train test split of A. The first array is always considered to be the training array, while the second, the testing one. Let's explore the result. First, it makes sense to check the shapes of the two variables. A train has a length of 75, while a test a length of 25. Here are the respective arrays. There are two important observations that we can spot right away. First, the default split is 75-25. Second, both arrays are shuffled. They used to consist of numbers ordered from 1 to 100, but are now completely randomized. In fact, these are the default settings of train test split. 75-25 is not an optimal split for my work, as I really don't like dedicating so much of my data to testing. To amend this, we can use an argument called test size and set it to a float between 0 and 1. Therefore, to achieve an 80-20 split, we need to simply include test size equals 0.2. Going through the cells below, we can see that we have successfully created an 80-20 split. All right! Sometimes, when working with time series data, for instance, the order of the array is of utmost importance. In these cases, we prefer our dataset to be split without being shuffled. There's an argument called shuffle, which is set to true by default. Changing that to false would yield a very intuitive result. The first 80 observations of A would be placed in A train, while the last 20 in A test. Okay, this is just some extra knowledge. In practice, most of the time, we prefer to shuffle the data. This removes time dependencies, day of the week effects, and so on. Usually, these are not crucial to causal relationships we are looking for and can only deteriorate our models. But more on that later on. For now, let's remove the shuffle argument. Now our results are shuffled again. What you may have noticed is that each time we run the code, we get a different shuffle. So the data is rearranged in a random manner. This is yet another issue for modeling. The main problem is that each time we split the data, we will get different training and testing datasets. So, if you are working on your models at home, you'd be creating a different regression on different data each time you run the cells. Training a model on different training data would generally have little impact, but it will have one nonetheless. For instance, your R-squared is likely to change with 1 or 2 percentage points, just because of the split. If you are trying to improve your model with many tiny tweaks, each of which are bringing 1 or 2% of additional explanatory power, a different shuffle every time would prevent an objective assessment of the changes. In the best case scenario, you would like to have shuffled data, but shuffled in the same way every time. Fortunately, SKLEARN has a random state argument. Let's see it in action. I'll add the random state argument and set it to 42. 42 is the conventionally used number by the community, a kind of an internet-y joke. If we try rerunning the code again and again, we would always get the exact same shuffled split. Okay, if we want to get a different shuffled split, we would simply change the random state to a different number. Let's try that out with 365. We got a different shuffled split, and no matter how many times we rerun the cells, the split doesn't change, while the numbers are still randomized. Okay, great! Finally, we must note that this method has another convenience. We can split more than one array at the same time. Here's where our B array comes into play. We can simply add B as an argument and include two new variables to store the returned arrays. We'll call them btrain and btest. By exploring the shapes and the arrays themselves, we reach a consistent result. A consists of the ordered sequence of the numbers from 1 to 100, while B from 501 to 600. Therefore, we can say that the number 1 from A matches with 501 from B, 25 from A matches with 525 from B, and so on. When we split A and B using the train test split, their elements are shuffled in the same way. Exploring A train and B train, for instance, shows us that they are indeed matching. This is extremely important for regressions because we want a certain observation's inputs to match with its target, even after shuffling. Okay, in our practical example, we will use this knowledge in practice. Thanks for watching.